So welcome to the next lecture of Math 120. Where is this camera setting? Let me check it. Yes. In the previous lecture, we were discussing about inverse of matrix, inverse of a matrix using elementary row operations. Elementary row operations. So we find a matrix by writing, just a second. We have considered an example. Let me see some other example. We can try it. Yeah. So if we are given a matrix of 3 cross 3, 3, 2, 5, and 4, 4, negative 2, negative 2. So this example we did in the previous lecture. How to find? We write another identity matrix 3, 2, 5, 4, 4, 8, negative 2, 2, 0, and an identity matrix of same order here. This. Then we try to reduce this A matrix into identity matrix and apply the same row operations on the identity matrix. This will be converted into the A inverse matrix. Now, why do we find it? Because finding inverse can help us to solve linear systems. You can say that solving linear systems by inverting the coefficient matrix. Solving linear systems by inverting coefficient matrix. Coefficient matrix. Now, if we are given any non-homogeneous linear system, AX is equal to B, then we can find first the inverse of a matrix. This is basically the coefficient matrix. If we can find its inverse, we can take it on the other side, or we can say that we multiply on both sides by A inverse from the left. So this thing becomes A into A inverse by the definition of inverse of a matrix. This thing becomes identity matrix. Identity matrix is equal to identity matrix into X is basically X. So in this way, we can solve a linear system by just multiplying the inverse matrix with the right-hand side vector B. So we can directly obtain the solution of a linear system. Similarly, if the linear system is homogeneous, AX is equal to 0, then if we can find the inverse of a matrix, if A is non-singular, then the homogeneous linear system can only have a trivial solution, which is a trivial solution. Now, two things which are very important here to notice that if this A coefficient matrix is non-singular, if its determinant is non-zero, in fact, its determinant is non-zero, then A is non-singular. I told you in the previous lecture what is non-singular, what are non-singular matrices. Or we say that A is non-singular, determinant is non-zero, or we can say A is invertible. All these things are same. A is invertible, A is non-singular, or you can say that A inverse exists. All these statements are equivalent statements. Okay. When the coefficient matrix is non-singular or it is invertible, then the linear system has only unique solution. Okay. It can have only one solution. Okay. When A is invertible, this nonlinear system has only one solution or unique solution. Okay. If A is invertible and A is square and as well as invertible, then the homogeneous linear system can only have a trivial solution. Okay, trivial solution only have a zero solution, or you can say trivial solution. Okay, so remember these things. If you have any question, you
Sir,
can ask.
could
जी
you
जी
repeat this? ये थोड़ा सर्क्यूट से गुजर गया, ये जो सिंगल सॉल्यूशन किसका ट्रिवियल किसका एक बार फिर से रिपीट कर दे.
देखिए ax is equal to b. This is your non-linear, linear system, non-homogeneous. If A is invertible, then you can take A on the other side. Okay, the first thing, A should be square matrix. Okay, means number of unknowns and number of equations are same in that linear system. A is a square matrix. A is non-singular, non-singular or invertible. Non-singular, when does a matrix is non-singular? When its determinant is non-zero. Okay. If this is so, then we can take A on the other side, as I told you earlier. Then we can find X is equal to A inverse B. Okay. In this case, the linear system can only have one solution. One solution. And what is that solution? We call it again a unique solution. Okay. If the linear system is homogeneous, okay, if the linear system is homogeneous, then the only solution is what? We can still have only one solution. And what is that solution? That solution is zero solution. And a zero solution is what? What we call it? We call it trivial solution or a zero solution. Okay. This is what? This is trivial solution, or we call it zero solution. This is what I was talking about. When the matrix coefficient matrix is invertible, we cannot have infinite many solutions. Okay, and solution must exist, and it has only one solution. That linear system. This is what I was talking about. If you have any other confusion, you can ask me.
Sir, kindly repeat that last line.
What should I repeat?
Sir, वो zero solution वाली और unique.
इसमें क्या समझ नहीं आया आपको?
Sir, there was a voice issue, so I couldn't hear.
Okay. If you have any linear system and you need to solve that linear system, for example, let me take some example. Any 3x3 matrix. This one, maybe. Let's do this example. Solve the linear system. Solve the linear system, and the linear system is 2x plus y plus z is equal to maybe 1, and 3x minus 2y plus 0 is equal to 2, and negative 1, so negative 2 plus x plus y is equal to 3. So this is your linear system which you have to solve. Now, what you do here, you write it in the coefficient in the form of a coefficient matrix 2, 1, 1, 3, negative 2, 0, and negative 2, 1, 1 times x, y, and z is equal to 1, 2, 3. Okay. Now this is your A matrix. Okay. This is your A matrix. This is your X matrix, for example, and this is your B vector. Okay.
Sir, can you please check the last row?
Can you?
Please check the last row in the matrix. I think there's a mistake.
Negative 2, 1, 1 is equal to 3. ठीक है ना यार? क्या problem है?
Sir, it's minus 2x plus x plus y.
जी x x y है.
Oh, sorry. ये y है, ये z है. ठीक है? It is z, obviously. Okay. So now this is your linear system. A times x is equal to b. Now what you do, you try to find the inverse of A first, which is 2, 1, 1, 3, negative 2, 0, and negative 2, 1, 1. and 1 0 0 0 1 0 0. I hope you can do it. After applying a series of row operations, you can get the inverse of a matrix. Okay, I hope you can get it. After finding the A inverse, if it is possible, okay, so this must be converted to the identity matrix. Okay, this must be converted to reduced to identity matrix when you try to convert it into reduced echelon form. And this matrix will be A inverse. Now, once you have A inverse, then in order to solve it, what you do, you just multiply A inverse with B, then you can get the solution. Okay, I hope you can do it yourself. This is how we solve the linear system. If we are unable to find the A inverse, then that linear system, we cannot use this method to find the solution of that linear system.
Excuse me, sir.
Ji beta.
So where did this identity matrix come from in the first step, where we've written A as a matrix and then line ki dusri side pe we've written the identity matrix?
Basically, the main idea, so the idea behind it is that definition of A inverse. What is the definition of A inverse? We call a matrix B is the inverse of A if its product from A, B, or B into A is basically equal to identity. Okay. Now, what you are doing here, if this is true, then you can write AB is equal to I, and you can take B on the other side. It means B in A is equal, sorry, or you can take A on the other side. In fact, then B is basically what? A inverse. Okay. Now, their product is I. Okay. Now, when you, this must be equal to this times I, you can say that. Okay. Now, we know that the product is I. When we write A here and I here, and we apply a series of row operations on both these matrices, we can even, in fact, prove it by using elementary matrices. That is not the, I think, exact explanation of this thing. We need to define elementary matrices in order to have a clear concept of this. Let me define what is elementary matrix. Then you can have an idea. For the time being, you just remember that it's a method that when you write A along with the identity matrix, you apply the row operations and try to convert that A matrix into a reduced echelon form. If it is converted into I, then the same operations would change I into the inverse of the matrix A. Elementary matrices are basically elementary matrices. What is elementary matrix? We need to define this in order to see why we do this. What is elementary matrix? If we have an identity matrix of any order, okay, it could be IN. Let me take example of I3. Okay. If we apply any one elementary row operation on this identity matrix, any one, okay, any one elementary row operation on identity matrix. Identity yahan pe it is identity matrix of order 3. Now you tell me which operation should I apply? There are 3 elementary row operation. I'm going to apply, maybe I'm going to interchange row 1 and row 2. Okay. For example, R1 is replaced by R2. The resulting matrix, which we obtain after applying exactly one elementary row operation on the identity matrix, I applied row 1 and row 2 interchange. So the resulting matrix is called elementary matrix. Okay. The resulting matrix is called elementary matrix. We can call it E1. This is the first elementary matrix. Now we can apply any other row operation on the identity matrix, and we get the elementary matrix, another elementary matrix, which may be different from this. Now the concept of applying row operations.
So,
GG.
So when we apply these elementary row operations on a identity matrix to get an inverse, वो हर step पे हमें एक elementary matrix मिलती है.
Yes, in fact. Again, I'm going to tell these things very briefly to you, just to answer the question of that girl, I don't know her name. If we have that matrix A is equal to 3, 2, 5, 4, 4, 8, -2, -2, 0. Yeah, the matrix which was in the previous example. Now, when we try to reduce this matrix into reduced echelon form, what we do? We try to make this thing 1. Okay, in the first row, first entry, we try to make it 1. Now, what elementary row operation you need here? You need 1/3 R1. Okay. When you apply this operation, this matrix will be what? 1, 2/3, 5/3. Okay, and all the other rows will remain same. Okay. Now you apply the same operation on identity matrix. What is your identity matrix? Of the same order: 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now the same operation you apply on identity matrix, and you get elementary matrix. 1/3 R1. You apply the same operation on it. You get 1/3 0, 0, 0, 1, 0, 0, 0, 1. So this is your let's call it E1. This is your first elementary matrix. Applying operation on this matrix, this operation, or you apply the same operation on identity matrix, and you get elementary matrix. This is equivalent to multiplying A with this elementary matrix. For example, you see this thing. You multiply A from the left with the E1. Okay, what is your E1? E1 is 1/3, 0, 0, 0, 1, 0, 0, 0, 1. You multiply this matrix with the A matrix: 3, 2, 5, 4, 4, 8, -2, 2, 0. This one. You multiply these two matrices and tell me what do you get? That girl who asked the question, what was your name?
Sir, Amna.
Amna. Huh. Now, you multiply this elementary matrix with the A from the left-hand side. What do you get here? 1/3 into 3, 1, 2/3, 5/3. ठीक है? पहली रो, बाकी रो वही हैं, वही रहेंगी. What did you get here? You get the same matrix here. Okay, which you obtained here by applying this elementary row operation on the given matrix. So there are two methods of applying elementary row operations. One is that you directly apply that elementary row operation on the matrix and you get the resulting matrix. The other one is the other method, which is more systematic, is you apply that elementary row operation on identity matrix, you obtain the elementary matrix, then you multiply elementary matrix to A from the left-hand side, you get what? That elementary row operation will be applied on that A automatically. Okay. Now, what is the next step? I hope you get this thing. If you have any confusion, you can ask.
Yes, sir, it's fine.
Now you have to make these two entries 0. Okay. You have to apply 2 more elementary row operations on this matrix. 1 elementary row operation on this in order to make it what? 0.
0.
You apply what operation do we need here? Negative 4R1 plus R2, and the row 2 will be changed. Okay. Now, I'm not going to apply this elementary row operation on this matrix directly. What I am going to do, I'm going to apply this operation on identity matrix. I will have another elementary matrix, E2, and then I will multiply E2 here from the left to apply this elementary row operation. Okay, and then get 0 here. Similarly, going in this way, all the elementary row operations can be applied on A to reduce it into what?
Echelon
To
form.
reduce echelon form. Reduce echelon form, sorry. Now, you can see that in order to apply first binary elementary row operation, I multiplied with E1, another E2, another E3, and so on. I apply K elementary row operations on A in order to reduce that matrix A into reduced echelon form. Finally, the A matrix has been converted into I3. Okay. The A matrix, when we multiply these elementary matrices with A successively from the left-hand side, finally A will be transformed into identity matrix if that matrix is invertible. Okay. Now we obtain this thing. Okay. Now, what is this? These are basically elementary row operations. And it is very easy to find inverse of these elementary matrices because it's almost identity matrix. Only one elementary row operation had been applied on these matrices. Now we can take these matrices on the other side, okay, one by one, or you can take them. You can take them together by taking its inverse, okay, on this side. Now A is what? A is basically what? EK, so on, E3, E2, E1, whole inverse times identity matrix. Now this whole inverse, using the property of a matrix, which is AB, whole inverse is equal to B inverse into A inverse, means this is basically, it will change. It's a kind of cyclic A, B, C, whole inverse. This will be what? C inverse, B inverse, A inverse. By using this property, what we can write here is basically E1 inverse, E2 inverse, E3 inverse, and so on, EK inverse times I. Okay. Yes. No. The thing which is more appropriate here, we should take A on the other side, not this thing. Now, if come back to this point, if this is true, then we can take this A on the other side by multiplying A inverse on both sides. EK, so on, E3, E2, E1, A times A inverse, we multiply on both sides A inverse from the right. So this thing becomes identity, which is multiplied again with the elementary matrices EK, so on, EK minus 1, so on, E3, E2 into E1 is equal to A inverse into I3. It becomes A inverse. Okay. Yes, that's fine. Now you can see here that what is A inverse? A inverse is the product of elementary matrices. And we had an I here, sorry, I here. Now, what is E1? It is elementary matrix, which has only one elementary row operation on it. Now, if we multiply this elementary matrix with I, and then E2, then E3, we multiply successively all the elementary matrices on I, then what do we obtain? A inverse. Okay. So that's why when we write A matrix here and I matrix here, and we apply same elementary row operations on I, which we apply on A in order to convert it into identity matrix, this will be converted into A inverse. So this is basically the idea behind that thing, this procedure. When we try to reduce this matrix into reduced echelon form, which is ultimately we should get identity matrix, and the same elementary row operations, when we apply on identity matrix, what do we get? We get A inverse. So this is basically the theory behind this procedure. So that is why we write identity matrix along with A, so that we can apply elementary row operations, which we apply on A, we apply same elementary row operations on I in order to get A inverse. Because we have seen by theory that this is possible. This will always be true. I hope you get it. Amna?
Yes, sir. Yes, sir, I get it.
Okay, that's good. Any other, if you have any confusion, you can ask me. So there was basically a concept of elementary matrices behind this method. Now, let's discuss finding other methods of A inverse, okay, and determinants. I told you in the previous lecture that there are two methods of finding A inverse. The first one is what? First one is finding A inverse by using finding A inverse by using elementary row operations. Elementary row operations. The second thing is by finding cofactors, using cofactors, you can say that. Cofactors and determinants and determinant of a matrix. First method we have already discussed. Now let's discuss the second method, finding A inverse. And also we'll discuss and finding A inverse and determinant of A. Okay. These both things are basically connected to each other, so we'll discuss them together. For this thing, we need to define some we need to understand some basic definitions about the matrix. For example, if we have a matrix, let's say A is a matrix, we take a general matrix, A 1, 1, A 1, 2, so on, A 1, N, A 2, 1, A 2, 2, so on, A 2, N, and so on, and so on, and so on, A N 1, A N 2, so on, A N N. Okay. This is a general matrix. We can write this matrix in a compact form as Aij N cross N, or in some books they write it in this notation as well, Aij capital brackets N cross N. Okay, where these indices Ij They are basically 1, 2, so on, n, and j is 1, 2, so on, n. Okay. So remember that this is basically a short form of expressing this matrix. Okay. In fact, when you vary the values of I and j, you should get this thing, an n cross n matrix. Now let's take a special case of this. I'm going to consider only a 3 by 3 matrix in order to explain you these concepts. Let us assume that we have A11, A12, A13, A21, A22, A23, and then A31, A32, and A33. This one. Now, what is a minor of a matrix? Minors. We need to define first minors. Okay. A minor of a matrix, basically corresponding to some element, is denoted by Mij, and it is you can say that a minor denoted by a matrix, you can say a matrix भी नहीं होता, ये determinant होता है, minor क्या है? A minor is denoted by Mij. Is the determinant of a matrix obtained by deleting ith row and jth column of A, of the given matrix A. For example, let's have an example. M11. M11 क्या होगा? It's this first index represents the row and second index represents the column. Now, what is this minor M11? Is the determinant of a matrix obtained by deleting ith row and jth column of A. Now, if it is M11, it is basically the determinant of the matrix A, what we obtained after deleting first row and first column. Okay. If we delete this first row and first column, what we are left with? We are left with these 4 entries. And what are these? A22, A23, and A32, A33. So this is minor M11. Okay. How many minors in this matrix we can find? One minor corresponding to each element. So basically M11 is a minor corresponding to A11, because it's the first row and first column. We can similarly find for example, 2, 3. Okay, M23 is a matrix is a determinant of a matrix obtained after deleting second row and third column in that matrix A. Now, what is second row and third column? A11, A12, A13, A21, A22, A23. Now, in order to find M23, what do? We delete the second row and third column. We delete these 2 things. What we are left with? A11, A12, A31, and A32. Okay. Similarly, we can find M12, M22, and so on, and the last one, M33. In this case, we have to delete third row and third column in order to get the M33, and it is what? It is nothing but A11, A12, A21, A22. So this is your M33. This is how we find the minors of any matrix. I hope you get it. Now, its determinant, M11 is a determinant of this thing, and we can find determinant of a 2 by 2 matrix. How can we find it? We multiply these two minus these two. Okay, the main diagonal, product of main diagonal entries minus the off diagonal entries A23 into A32. So this is basically, we can find minors, okay, if we have a 2 by 2 matrix. This is how we find the determinant of a 2 by 2 matrix. I hope you get it. If you have any question, you can ask me. The next thing which we need to define here, which we need in order to find the A inverse using cofactors, is a cofactor. Okay. For the similar 3 by 3 matrix, how do we define a cofactor of this thing? Let me write it here. Now, cofactors corresponding to entries of a matrix, entries of A matrix. Now, again, A is what? Again, I'm considering again the third 3 by 3 matrix, A11, A12, A13, A21, sorry, A21, A22, A23, and then A31, A32, and A33. Now, how do we define the cofactor? Cofactor is denoted by basically, a cofactor is denoted by cofactor corresponding to the element, the entry, you can say the entry A, general entry को अगर हम कहें तो चलें कोई भी कह लें, entry A11 is denoted by C11 and is defined by C11 is equal to A11 times, sorry, not A11, corresponding to A1 is denoted by C11, and it is minus 1 raised power 1 plus 1 times M11. Okay. So if we take any general element, which we had written here, a matrix, general matrix, this one. So its general element is Aij. If we write this cofactor for any general element Aij, then it would be Cij is equal to minus 1 raised power I plus j times Mij, where Mij is what? Is a minor of that matrix corresponding to Aij. Okay. So this is basically a general definition of a cofactor. Now, where Ij, if we have an n cross n matrix, the variations of I and j are 1, 2, up to so on, n. Similarly, j is equal to 1, 2, so on, n, because it's a square matrix. So here, how many cofactors we can find? This is basically -1 raised power I plus j. It's a composition of sign, writing a cofactor corresponding to some element aij. Now, if we want to find C1, let's discuss this with the help of some example. Let me take the same or this one, this matrix. Let us discuss these things with the help of example. Now, consider this matrix 2, 1, 1, 3, -2, 0, -2, 1, 1. So this is our matrix. We are going to find all the minors and cofactors of corresponding to this matrix. Okay. But you can find directly cofactors because I hope you know what is a minor, so we will write minors directly. So we are going to find all the cofactors. What is C11? It is -1 raised power 1 plus 1 times minor M11. M11 is what? It is M11. So -1 raised power 2 is +1, and -1 is what? We delete the first row and first column, and we obtain this matrix. It is -2, 0, 1, 1. And what do you obtain here? -1 raised power 2 is 1, -2. So it is -2. Okay, this is your C11. Now C12 is what? -1 raised power 1 plus 2, M12. Okay. It is what? -1 raised power 3, M12, first row, second column. First row, second column. So what do we obtain? We obtain these 4 entries. So its determinant is 3, 0, -2, 1. So what do we obtain here? -3. -3. Now you people find all these cofactors and tell me the values. Hurry up.
Sir, a question है.
जी जी.
जो आप राइट पे मैट्रिक्स लिख रहे हैं उसको माइनर करके ये आप उसका डिटरमिनेंट लिख रहे हैं या आर यू राइटिंग द मैट्रिक्स इटसेल्फ? आई थिंक डिटरमिनेंट लिख रहे हैं ना.
Yes, I'm writing determinants. I told you that the minor is a determinant of the matrix which we obtained after deleting ith row and jth column from the given matrix A. Minor is basically a determinant.
Sir, can you put the previous board for just
जी,
2
जी,
seconds?
ये ले. Yes.
Okay, sir. Thank you.
Okay, now you tell me all these cofactor things. What is C13 and C21, 23, 22, 23, and C1, 32, 33? You tell me all these values. I'm waiting for that. What is your C13?
It would be 2.
First row, second column. 3 minus 4. Again, first row, third column, आप delete करेंगे, you get this thing. इसका determinant क्या होगा? 3 into -3 minus 4. तो ये -1 नहीं होना चाहिए. इस तरह C21 is what? Second row and first column आप delete कर देंगे. Second row, first column. You get what? This and this. 1 minus 1, it is 0. Okay. And C22 is what? You delete second row and second column. Kindly mute your mic. Second row, second column. You multiply this and this. 2 minus -2 is +2, 4. 4 is C22, 4 aa jayega. C23 would be what? Second row, third column. I delete kar rahe hain. Second row, third column. So 2, 2. +2 minus -2, 4 आ जाएगा. ये भी 4 आ जाएगा. लेकिन -4 होगा क्योंकि 2 और 3 है यहाँ पे, तो -4 आ जाएगा. फिर C31 is what? You are going to delete third row, Third row, first column. You get 0 here, you get +2 here. So this is 2. So 3, 2 is what? Third row, second column. Now you are deleting these two things. You get 0, -3. -3 or +3 हो जाएगा. Okay. And C, 3, 3 is what? You're deleting here, third row, third column. You get -2, -3, -5. It is -5. So these are all the cofactors. Now you
Sir?
put them all in a matrix. जी बोलो.
सर C223 नहीं आ रहा क्योंकि हमारा जो
C22.
मैंने आपका
देखिए,
3 0 -2 1 आएगा ना
C22. ये आपने सेकंड रो, सेकंड कॉलम डिलीट कर दिया. But you are left with 2,
अच्छा,
1,
सही, सही।
-2, 1. 2 ones are 2,
जी, जी।
-+2, 4. Okay,
सही मैं
you get this.
यस
Now you put all these cofactors in a matrix. See, C11 is -2, C12 is -3, C13 is -1, C21 is 0, C22 is 4, C23 is 4, negative, C31 is 2, C32 is 3, and C33 is -5. This one. This is what? This is a matrix of cofactors. Is a matrix. It's called a matrix of cofactors. Okay, cofactors, and it is usually denoted by C. And yes, we are going to find A inverse. Yes, I remember.
सर एक इन्वर्स निकालने के लिए आपको हर एक चीज का निकालना पड़ेगा कोफैक्टर.
जी जी जी. ये सारों के हमने पहले कोफैक्टर्स फाइंड करने हैं. ठीक है, फिर उसके बाद हमने डिटर्मिनेंट भी फाइंड करना है. अभी हमने डिटर्मिनेंट फाइंड ही नहीं किया. ठीक है, देखना है अभी हमने कि डिटर्मिनेंट कैसे फाइंड करते हैं. अभी तो हमने सिर्फ कोफैक्टर्स फाइंड की. अब आपको पता है कि फार्मूला क्या होता है फाइंडिंग ए इनवर्स का. A inverse is what? 1/, determinant of A times adjoint of A. ये होता है ना. 2/2 मैट्रिक्स का इनवर्स का फार्मूला आपने पढ़ा होगा, यही वाला. Anyone? सबने पढ़ा है ना?
Yes, sir.
Okay. Then what is this adjoint of A here? Adjoint of A is C transpose. And what is C? C is the matrix of cofactors of A. Okay? You take the transpose of that matrix, this one, which is a matrix of cofactors, you take its transpose. Transpose kya hota hai? I told you. You put all the rows in columns. Okay? You interchange rows and columns of any matrix to get the transpose of a matrix. So you can find adjoint of A in this way. What we have done above is basically is all the work for finding only the adjoint of A. Okay. Now, next thing is how to find this determinant. How to find this determinant. Determinant of this matrix is basically can be computed using cofactor expansions along rows or columns, along any row or along any column. Okay, I'm going to write it here. This adjoint of A is what? I told you it's basically C transpose. Okay. Now we are going to discuss finding determinants using cofactor expansions. Okay. Now, what is a cofactor expansion? For example, first हम लिखते हैं cofactor expansion along first row. Cofactor expansion along first row. Okay. Remember this. We can write cofactor expansion along any row. Okay. The first thing, just to understand it, I'm going to write the first cofactor expansion along the first row. Now, what is first row here in this matrix? Let me rewrite it properly. This one, this one, this one. See. Now, this is the first row of a matrix. How do you write cofactor expansion along first row? And this will give us determinant of A. So determinant of A can be calculated by writing cofactor expansion along the first row. How? This is your first row, A11, A12, A13. Okay. If we generalize it, let me write the general definition of this thing. And so on, the first row, the last element would be 1n. Okay, A1n. A11, 12, 13, so on, A1n. We write the corresponding elements A11 times C11 plus A12, C12 plus so on plus A1n, C1n, where A11, A12, A1n are the elements of that matrix, and C11, C12, so on, Cn are what? They are cofactor matrices. Okay, so we have written an expansion, cofactor expansion along the first row. So that is why it is called a cofactor expansion. How we are going to write this in a more compact form? You can see here that in the first row, ith index is fixed 1. What is varying here? The j. J is 1, 2, 3, so on, n. So I'm going to write it in the sigma form, sigma or sum. J is from 1 to n, A1j, C1j. So this is how I can write the cofactor expansion along the first row for in order to find the determinant of the matrix A. Similarly, we can write cofactor expansion along any row. For example, you have some ith row here, AI1, AI2, AI3, so on, AIN. So in that case, यहाँ पे क्या हो जाएगा? 1 की जगह I हो जाएगा. So this is AIJ, IJ. I will be fixed here. I is fixed. Okay, I will be fixed here. I can be what? 1, 2, 3, so on, n. Whatever the value of I you fix here, you get an expansion along that row. So this is how we can find the determinant of A by writing a cofactor expansion along any row. So now you know what are your cofactors. You have C11, C12, C1n, and you have elements A11, A12, AN. So you can find the determinant of A. For example, in that above matrix, this one, if you want to find the determinant of this matrix, how do you find it? Determinant of this matrix is what? Along the first row, 2 times C11. What is your C11? It is -2 plus 1 times C12. It is -3 plus 1 times C13. It is -1. Okay. So you get this. So now after solving this, you get -4, -3, -1. So -4, -1, -8. This is the determinant of that matrix. So you can find determinant by using cofactor expansion along any row. So this will be the determinant of this matrix. Now you have determinant, you have adjoint of A, you can find the inverse of this matrix by putting adjoint of A here, determinant here. You can simplify this, you'll get the inverse. I hope you get it. If you have any question, you can ask me.
सर इधर
Go ahead.
थैंक यू.
Yeah.
तो मैं पूछा था सर, इधर एक हमने बेसिकली रो एक्सपैंड करके हमें डिटरमिनेंट मिल जाता है. किसी
हाँ।
रो को एक्सपैंड करके ले सकते हैं।
डेफिनेटली किसी भी रो को वो आपने डिसाइड करना है। मसलन यहाँ पे आपके पास एक बहुत बड़ा मैट्रिक्स है, ठीक है, यहाँ पे 1 2 3 4 5 7 8 9 0 8 10 11 10 1 -5 0 4 नॉट 0, यहाँ पे भी 0 कर लिया, ठीक है, यहाँ पे फिर -5 7 11 3 4। अब मैं किस रो को चूज करूंगा जिसमें 0 से ज्यादा? डिटरमिनेंट फाइंड करने के लिए मैं इस रो के अलोंग एक्सपेंशन फाइंड करूंगा ताकि मेरी जो कैलकुलेशंस हैं वो आसान हो। ठीक है,
सर और सॉरी एक दफा फिर से उसको रिपीट करने के लिए, इधर एडजॉइंट क्या होगा?